Good evening, people. I welcome you all on the fifth live session of our NPTEL course, which is Ultrafast Laser Spectroscopy, taken by Professor Anindya Datta. I am Shruti. I am one of the PMRF TAs of the course, and today we will be discussing our assignment number 4. So it's 7 o'clock now. We'll wait 5 minutes for a few people to join and then we'll start. So we'll begin the discussion. So assignment 4 has the date for submission of assignment 4 has crossed already, and NPTEL has given the answers of the question. So we'll just discuss how to solve we'll discuss the solution. We'll go through each question and discuss all the options and the answers too. So the first question asked was stimulated and spontaneous emissions respectively are coherent and incoherent, omnidirectional and unidirectional, unpolarized and polarized, polychromatic and monochromatic. So uh, we'll first see what are spontaneous and stimulated emissions. So first we'll discuss this, what is coherent, collimated, polarized, polychromatic. Polychromatic and monochromatic, this thing I had already discussed in the live session 3. So a coherent and collimated light is in phase. Coherent means in phase and collimated means they are parallel. See, they are moving parallel. So all the beams are parallel to each other. But coherent means in phase. These beams are in phase again, but they are not collimated because this beam is going in this direction and this beam is going towards this direction. So they are not collimated. Incoherent beam means they are out of phase. Out of phase. See, you see here, this is minima here and this is maxima, almost reaching maxima, so they are not in phase. And again here it is this minima and this maxima is coming on top of each other, so these types of beam are called, they are out of phase and hence incoherent. But they are collimated because they are moving in the same direction. They are all parallel rays, so they are collimated. And here is an example of a beam which is collimated. Collimated means moving in the same direction, are parallel beams, but they are not monochromatic. Now monochromaticity means they should have same wavelength, or see here the wavelength is, if we'll measure from here to here, so the one wave is from here to here. This is one wavelength, but from here to here it has many, the second wave has many wavelengths, so they are not monochromatic, they don't have the same wavelengths. So these waves are called polychromatic, like the fourth option, polychromatic. Okay, so what is the gist? Coherent ones are in phase. Collimated means moving in the same direction, like the parallel rays. Uncollimated or not collimated means moving in different directions. Incoherent means they are not in the same phase, they are out of phase. Okay, so let's see what is spontaneous emission and stimulated emission. So spontaneous emission is when we'll excite a molecule, we'll give some excitation energy. The molecule was in this ground state and this is excited state. So when we are exciting the molecule, it will go from ground state to excited state. Okay, but it won't stay in excited state for a long time. because excited, all the states will have a lifetime. Excited state also has a lifetime, so the molecule will come down back to the ground state, which is the most stable state. So when it comes down to the ground state naturally without doing anything else, so that emission is called spontaneous emission. Excited state, ground state. So it is, so this one is called spontaneous emission. Spontaneous means immediately or quickly, automatically. So this one is, we are not giving any extra energy for this molecule to come down to the ground state. So the definition of spontaneous emission is, spontaneous emission is a result of transition of an atom from the excited state to the lower state, which happens due to the natural tendency of the atom to attain minimum energy. So it is the natural tendency of the atom or molecule to come back to the ground state, to the most stable state. Ground state is the state with minimum energy. Okay. But what happens for stimulated emission? We'll see. I'm not doing slideshow mode here. It's easier to change and add slides here. So in stimulated emission, so first we'll give some extra energy to this atom or molecule. We'll give it some energy h nu, and it will go from ground state to excited state. Stimulate means to poke. So we have to now poke this molecule or give it some extra energy and force it down from excited state to ground state. So it won't come out naturally on its own. So we have to give it some extra energy. We'll, okay, I have to make this dotted. So we'll give it some extra energy, we'll give, and then it will come down to the ground state. So why it won't come down automatically? So if this excited state has longer lifetime, so the molecule is staying there for a long time. And if we want the molecules to come down before its lifetime, so we have to give it extra energy to come down to the ground state. But when it will come down to the ground state, it will emit two photons. One photon which we are giving, this is h nu, and one more photon which will be in phase with it, which is h nu, which is equal to the difference between these two levels. Okay, so this one is called stimulated emission. We are stimulating the molecules to come down. So the definition for stimulated emission is, stimulated emission of radiation is the process in which photons are used, external agents like photons are used to stimulate atom in the excited state to fall down to the lower energy state. Okay. In spontaneous emission, we were not giving any extra light for the molecule to come down. No external agent is involved. But in stimulated, we are giving external photons. Okay. The results of spontaneous, now both are radiative process. So when spontaneous emission happens, the emission is like ordinary light. So last class we had discussed the properties of ordinary light, right? It is not collimated, and the beams are not in phase. So same here, the spontaneous emission is ordinary light, and the light obtained is not coherent. They won't be in phase, moving in random directions, no, incoherent, and um, not collimated. So here we'll write incoherent. Oof, why it is getting erased every time? Some problem with my pen. Incoherent and non-collimated. But the emission which comes out of the stimulated one, these two waves will be highly collimated. This wave which came out as a result of stimulated emission will be collimated with respect to the incident, with respect to the external photon which we kept. So this will be collimated and coherent. So this one can be used for lasers. So lasers are, last class we discussed about the properties of lasers. So lasers are give monochromatic light. They are coherent. All the beams are in phase. They move. They are collimated for a long distance. Like all the beams move parallel to each other for a long distance. They do not spread. So all these properties coincide with these properties of stimulated emission. So for lasers, we use stimulated emission and not the spontaneous emission. So if in a laser spontaneous emission is happening, we don't want that. That is bad for a laser. So lasers use stimulated emission. Now come back to the question. The question asked stimulated and spontaneous emission respectively are. Now I think you can just answer the question. They are stimulated emission is coherent, true. Spontaneous emission incoherent, that's also true. Stimulated is omnidirectional. Omnidirectional means present in all the directions, but not. We just discussed stimulated emission is like this. It is going in this direction only. Maybe if the light propagation is this z direction, it is going in this direction, not in minus z, not in x, not in y. Okay, so it is unidirectional. These are written in reverse order. It should be here and it should be here. So this option is wrong. It is unpolarized, false. The emissions will be highly polarized. Spontaneous emissions will be unpolarized because it is happening in all the directions. So the polarization of the light will get cancelled away. Polychromatic, monochromatic. No, this is a monochromatic. Both can be monochromatic. So the correct option will be option A, coherent and incoherent. Okay. So I think the question is clear now. Let's move to the next one. So the next question is about Einstein's coefficient. It is asking the correct statement among the following about Einstein's coefficient. So let's discuss what these coefficients are first. We have A12. A12 will be, let me draw the diagram here first. So these are two energy levels for a molecule: ground state, excited state. Energy level 1, 2. Okay. So when we'll give it some energy of frequency nu12, it will undergo excitation and it will go to this energy level 2. The rate of this will be is given by B12 rho 12 nu n1. B12 is the Einstein's coefficient for absorption, rho 12 energy density, n1 is the population of state 1. Okay, then this is excitation or absorption. Okay, it will take energy, then it will, this is spontaneous emission. Spontaneous emission will, the rate is given by A to 1 happening from second level to first level. So A to 1, and it will depend upon the population of energy level 2. So N2. Then third will be stimulated emission. Okay, and it will be given by B21 rho 12 nu into N2. The energy density is coming because this will happen when we will give some external photon of the same energy level. Okay, so this is the energy diagram. Now in the question we are asked A12. A12 I didn't show here. A12 will be just spontaneous absorption. Spontaneous absorption. The absorption which happens on its own without giving any energy. So this will be obviously very less probable, or very less probable. Okay, so this will come the least, rate is least. Hello Ishika. Okay, now what is B12? B12, this is Einstein's coefficient for absorption again, but this time stimulated absorption. And B21, this is Einstein coefficient for stimulated emission. Okay, so we have to get a relation between these two, and let's take a new slide. And at steady state, to solve a relation between these two, what we will assume that at steady state, when both these rates are happening, when the system is in equilibrium, okay, so the population of this level, the change in population of this level is 0. So at steady state, dn2 by dt is equals to 0. So now we know how to write the rates from chemical kinetics. We'll write, so the process which is sending the population up and which is depopulating the state. So this should be equal to the sum of these two, right? So that's what we have to write, that B12 rho 12 nu N1 should be equal to B21 rho 12 nu N2 plus this is A21 N2. This is spontaneous emission part. Spontaneous emission. This is stimulated emission part. Okay. Now little bit rearrangement. So rho 12 nu will be B12 N1 minus B21 N2 is equals to N2. So we can write rho 12 nu is equals to A21 N2 divided by okay. Now divide everything like denominator and numerator. Divided by B21 N1. Like we will divide by this factor. Okay. So it will be B21 N2, right? N2. So it will be N2 will get cancelled. Here we will get A21 by B21, and in the denominator part we will get B12 by B21 into N1 by N2 minus 1. This term is this term itself. Okay. So, and what we know, we have from Boltzmann distribution, how the population of the two states will be distributed. This is from statistical mechanics. E minus h nu 12 divided by Boltzmann constant times T. So here what we need, N1 by N2. So we will reverse the relation. N1 by N2. On reversing, this minus sign will go h nu 12 by kBt. So this thing we can put back on that equation. We had rho 12 nu is equals to A21 divided by B21 whole divided by B12 or 21? B12. Yeah. B12 divided by B21 e to the power h nu 12 kBt and minus 1 of course. So now can you just guess from which this whole equation looks similar to one equation which we study in Planck's radiation theory, which is this 8 pi h nu 12 cube divided by c cube e to the power h. I'm writing here nu 1 2 because we are taking the energy level 1 and 2. That's why. Otherwise it will be simply nu divided by kBt minus 1. So when you will equate these two equations, the numerator part we have minus 1 here, we have this part here, exponential part. So from here what we will get, when you will equate you will get B12 divided by B21 equals to 1. Okay, so in this relation we have only 1 here before exponential, so this part is equals to 1. So from here we can get that is equals to, so both these Einstein's coefficient is equal and we can give it to equal to some constant b. Okay, so this answers our question here, that we have B12 equals to B21. So in these two options we have this, and it is showing it is equal to A12 also. But I told you A12 is the rate of is the Einstein's coefficient for spontaneous absorption. Spontaneous absorption is very a rare event, less probable. So the rate of this should be obviously less than these two rates. Okay, so the answer should be D and not A. Okay, so this answers the question. Let's move to the next one. Yeah, so I have shifted the fourth question up after the second one because the answer for this question is related to the derivation which we did just now. So it is asking, for a two-level system, the ratio of populations of the higher and the lower energy states must be equal to or lesser than. These five options are given. Okay, so we have to find the ratio of population of level 1 and 2. So ratio of population of 1 and 2, that is N1 and 2 relation we have to find. Okay, so for a two-level system, so here we have a two-level system. This is 1 and this is 2. When net stimulated emission will happen, so for net stimulated emission, okay, because we need net stimulated emission. Net stimulated emission, why we don't need spontaneous? Because spontaneous emission won't give lasing, so we want net stimulated emission, and this will happen when here, when the rate of this one is more than this one. Okay, then it will be net stimulated. We are neglecting the spontaneous emission part here. So the rate B rho 1 2 nu, and we can write, instead of B1 B2 we can write B now, because we saw in the last question that B12 is equals to B21. So this should be greater than B rho 1 2 nu N1. Okay, so this means N2 should be greater than N1. So this is our relation. But the question is asking to quantify the ratio between these two. So for a two-level system, we will assume that the total population N total the total population of the two states is sum of population of both the states. Okay, so we can write from here n2 by n1 should be greater than 1. Okay, so you can write n2 is equals to 0.5% of the total. Okay, for a two-level system, the ratio of population for the higher and lower energy states must be equal to or lesser than I think it should be greater than, must be this, if they are asking this, the ratio of population must be equal to or greater than 1. Yeah, okay, so this solves the fourth question. Okay, let's move on to the next one. So the third question is, you have patented a new gain medium for lasers using vibranium. Energy level diagram is shown here. So it's a hypothetical question that you have a material called vibranium in which the energy levels are as shown below. So the output wavelength from laser of this material is coming at 496 nanometer. So at which transition lasing is happening? Which is the following transition is responsible for the output light? So at which transition lasing is happening? This is the question. So let's take a new slide. Now let me first write here the energy differences which they have given in the options. Okay, so E1 to E2, so here is E1 and here is E2. So if the transition is happening from here to here, the energy difference will be -8 minus 4 electron volt. So this will be minus 4 electron volt. E1 to E3, E1 and E3. So it will be -5 minus 1.5 minus 8, that will come 6.5 electron volt. So this one will be E4 to E2. So here is E4, here is E2. So it will be -4. So it is coming from E4 to E2, -1 minus 4. -1 minus 4. This will be 3 electron volt. Fourth option is E4 to E3. E4 to E3. So it is -1 minus 1.5, which is 0.5 electron volt. Now option E is E3 to E2. E3 to E2. So minus 1.5 minus of minus 4 volt, which is 2.5 electron volt. And the last option is E2 to E1. So it is the reverse of first. So instead of -4, it will come at 4. So because the energy levels are same, 4 electron volt. Okay. So we have now what we have to do is the output wavelength is 496 nanometers. So output is given in the wavelength, and we have to get the energy associated with this wavelength in terms of electron volts. Okay. So let's see how to do that. Okay. Now we know energy is given by Hc by lambda. Okay. So let's put the values of the constants. H is 6.626 into 10 to the power minus 34 joule seconds into speed of light 2.998 into 10 to the power 8 meter per second divided by lambda. Just for now we'll keep lambda as lambda only in meters. Okay. On multiplying these two, you will get 1.986 into 10 to the power minus 25 joule meter, because seconds will get cancelled, divided by lambda in meters. Then meter will get cancelled and we'll get it in the unit of joule. But we know 1 electron volt is equals to 1.602 into 10 to the power minus 19 joule, right? So to convert this energy in joule to electron volts, we will divide it by electron volts. Okay. So we can divide the whole thing minus 25 divided by lambda in meters. You will get to know why I am writing in meters every time, because we have to change the unit of that lambda. 10 to the power minus 19 joule got converted into electron volt, and meter will remain meter here. Now we will convert this meter also. Let's first divide these two to simplify. So it will into 10 to the power minus 6 electron volt into meter divided by lambda in meter. Okay. Now when these meters will get cancelled, we will get the unit as electron volt. That's why I am writing here meter every time. Now we will, okay, now we have to convert the meter. We'll write 1 meter is equals to, because the unit given in the question is in nanometers, so I'll convert the wavelength into nanometers. So 1 meter is equals to 10 to the power 9 nanometers. I will box this up. So I will put here, now wavelength I will change to nanometers, into 10 to the power minus 6 electron volt into, instead of meter I have to write 10 to the power 9 nanometers. And now to cancel this out, this wavelength here, it should also be in nanometer. Okay, so these will get cancelled out. Now solve this up and you will get 1.240 minus 6 plus 9 is plus 3, and when you will multiply it here, you will get it 1240. So I am writing it simply. So this is 1240 divided by lambda in nanometer only you have to put. So if you will put it here in meters, the answer will get wrong. So this is the energy. Now the wavelength given in question is, lambda given is, how much it was? 496, right? So let's write this 496 nanometer. Now answer will be energy is equals to 1240 divided by lambda electron volt. Now keep the values. 1240 divided by 496 electron volt. When you will divide this, you will get this at 2.5 electron volt. So the energy difference between the two levels through which lasing is happening should be at 2.5 electron volt apart. Okay, so let's see which is at 2.5 electron volt. So here 4, 6.5, we have this one 2.5 electron, Eth option, which is E3 to E2. So the lasing is happening between these two levels. Okay, so this is the level in which the transition related to lasing is happening. Okay, so that's how we will solve this question. Okay, I hope it got clear now. So let's move. So let's move to the fifth question. The correct statements among the following are: 3-level lasers are CW. CW is continuous wave. 4-level lasers are pulsed. 3-level lasers are pulsed. 4-level lasers are continuous wave. Both 3 and 4-level lasers are CW. Both 3 and 4-level lasers are pulsed. So now we will discuss first what is this 3-level and 4-level. So here I have a drawing for a 3-level system. 3-level means there are 3 energy levels in the system, in the molecule. And 4-level means there is one more extra level just above the ground level in comparison to the 3 level. Okay. So here lower laser level is the ground state. Lower laser level is ground state. And here lower laser level is, this is the lower laser level and it is above ground state. Okay, so let's name these levels first. E1, E2 and E3. So it's a 3-level system. This one is 4-level. So E1, E2, E3 and E4. So here lasing is happening. In this case, lasing is happening between E2 and E1. That's why I have written that the lower laser level, which is E1, is also the ground state. And here lasing is happening between E3 and E2. So the lower laser level is above the ground state. Ground state is here E1. Okay. So that's the difference. Now what happens in 3-level? This, we will excite the molecule. It will take up energy and go to E3 state. Okay. And here we are not discussing anything about spontaneous emission. We are assuming there is no spontaneous emission, just the stimulated ones. Okay, for the sake of simplification only. So we are exciting, the population will, E3 level will get populated. Okay, and from E3 it will go to this um, this energy level E2 via some non-radiative transition. This one is non-radiative. That's why it is kept in dotted line. Non-radiative. Okay. Here, this lifetime, let's write that this energy level has a lifetime of 10 to the power minus 8 seconds, and this level has a lifetime of 10 to the power minus 3 seconds. So in which state electrons will stay for a sorry, not electrons, molecules or atoms will stay for a longer time, which has a longer lifetime. So the energy level E2. So when you will pump the laser, it will uh, get excited and go to E3. But as the lifetime of this level is very less, all the levels will come down. Sorry, all the molecules will come down via some non-radiative transition to the energy level E2, and it will, because it has a longer lifetime, it will get collected here. So we can show the molecules being, it's like a bin which is collecting all the molecules. So until the population of this E2 energy level is so much that it cannot take up more electrons, so when you will pump again, all these molecules which are there will come down at one go to energy level E1 via radiative, and they will give lasing. Okay, so everything will come down at one go. So this will give lasing. This stimulated emission will give lasing. So the process will again be repeated. Here some molecules are there, and you have to pump, 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 keep on pumping until this E2 energy level is more than E1 and everything is coming down at one go. So what is happening here? We will get a pulse. For example, my drawing is bad here. We'll get the pulse, and again we have to wait for some time until this level is being filled. Then when this population is, we reach population inversion state, that is population of E2 state is more than E1, again we'll get a pulse. Okay, so like this the process, the cycle will go on and we will get lasing. So we can see here what we are getting. We are getting a pulsed laser. So three level system is giving a pulsed laser. Now what happens in the four level system? Here we have one more state. Lasing is happening between these two. When you are pumping, this also has a smaller lifetime. The everything is being collected here. But what happens here, this E2, this one has negligible lifetime or like very small lifetime. How do I write that? Very, very short lifetime. Okay, so as it has a very short lifetime, molecules are not staying, even if they are coming at this state, they are not staying at this level and they are going down here at E1. So the we don't have to wait here at this in this system for the for population inversion scenario to reach, because here at all times population inversion is there. E3 level is always more populated than E2 level, because molecules are not residing at E2, because it has a very small lifetime. They are coming down. As soon as they come to E2, they are coming down to E1 very fast. So we need very small amount of pumping to create lasing here, and this process goes on continuously. Here we don't have to wait. This wait period was to get the population inversion scenario, but here population inversion is always present. Population inversion is there at all times, which means n3 at time t is always greater than n3 at time t. At any time, the population of E3 state is more than E2 state. So we don't have to wait here. So when we will get here a continuous lasing we will get. So this is here a 4-level system giving CW lasers. So this answers the question that 3-level lasers are pulsed and 4-level lasers are continuous wave lasers. So the correct option will be option B. Okay. I hope the question is clear. So actually there is no one in the class, but I'm sure you guys are watching the recording. It's being uploaded on YouTube, and the link for that YouTube videos are there in the Ultrafast course. You can find them under the live session panel. In the course content you can find live session, and there a Google Drive, Google Sheet will open, and you can, from there you can watch the videos weekly, like week wise the videos are uploaded there, and also these slides are also there, so you can just, if you don't want to watch the video, you can go through the slides. So we, till now we have discussed up to 5. Let's move to the next one. In a HENI laser, so in a helium neon laser, both helium and neon are energized directly by electrons. Helium is energized by electrons and transfers the energy to neon. Neon is energized by electrons and transfers the energy to helium. So, helium neon laser has been discussed by sir slightly. So, what happens in these lasers? Helium we will excite, so we will get helium ions and few electrons. Okay, it will go to excited state, we will have helium plus and electrons. So these ions and electrons, these, the electron which comes after ionizing helium, they hit the neon. Okay, so helium is energized. Okay, so here, what happens here? Sorry, what I said was wrong. We excite helium first. So how do we excite only helium? Because we will excite it at this particular wavelength, this particular energy. So only helium is getting excited, and when it is getting excited, they have almost similar energy level. So they, when these two ions bombard, helium ion neon atom, when they bombard, they they exchange energy. Okay, so this also gets, neon also gets excited. So helium is energized by electrons. Helium is energized by electrons, and then it transfers energy to the neon. So the correct option will be option B. So in the HENI laser, the lasing happens due to neon, but neon gets excited because of helium energy transfer from helium. So lasing is this maybe this, or sometime we use this too. This is the lasing wavelength. Okay, so the answer to this question will be helium is energized by electrons and then it transfers the energy to neon. So here you can see collision with the excited helium atom, which gets collision with excited helium atom and neon. Helium transfers its energy to neon. Okay, so let's move to the next one. The next question says, if L is the length of the cavity of a laser, n is the integer, lambda is the wavelength of a longitudinal mode, then what is the relation between these three terms? Okay, so it is asking the relation between the length of the cavity, the wavelength, and the number of modes, which is n. Okay, so for that here, for the derivation, I have a picture here. So in the first picture, you see this is our laser cavity. This is which is bounded by these two green blocks. It is our laser cavity. So and this is a wavelength of light. When light here from here, this is not one wavelength. This is what a half wavelength. So when it will go here, then it will complete one complete wavelength. Okay, so it is half wavelength. So what is happening here? I can write that here lambda by 2 is equals to L. So half wavelength is equals to L. L is here, which is the length of the cavity, this cavity length. Lambda by 2 is equals to L when the number of modes one. Now in the next case, what is happening? This is one complete wavelength. Okay, so here lambda is equals to L. I can also write it like lambda equals to L, so I can write it like 2 times lambda divided by 2 equals to L. Okay, so both means the same. In the next scenario, what is happening? This is one wavelength and this is another half. So it is 1 plus half, so which is 3 by 2. 3 times 3 by 2 I can write like this is equals to N. Okay, so 3 by 2 wavelength is equals to the length of the cavity. In the next scenario, we have 1 and 2 wavelength. So 2 lambda is equals to L. So now 2 lambda, can I write it like this? 4 divided by 2. Okay. And in the next case, we have 1, 2, 2 and half. Okay. So we have 2 and half, so which is 5 lambda by 2 is equals to L. So you see here a pattern, lambda by 2, lambda by 2, lambda by 2, lambda by 2, here also lambda by 2, and we have integer counts coming here 1, 2, 3, 4, 5. So here you can write a relation like L is equals to n lambda by 2. So this is the relation between the length of the cavity, the wavelength, and the number of modes. N is equals to integer 1, 2, 3, 4, which is the number of modes. The number of modes logged in the laser. So we got the answer for the question. If L is the length of the cavity, N is the integer, lambda is the wavelength of light packed in the cavity. So we have L is equals to N lambda by 2. So answer is D. Okay. So I have a very quick question over this. The question, this numerical question, it says that you have a AlGaAs. So this is a short form for aluminium gallium arsenide. So it's a semiconductor which it's a semiconductor laser which has a cavity length of 350 micrometers. Sorry, this M should be small. 350 micrometers, and it has the wavelength of light inside is 800 nanometer. Then calculate the number of wavelength that will fit in the cavity. So here we have to calculate the number of modes logged in the cavity. So we can use the same relation, since L is equals to n times lambda by twice. So n is equals to 2L by lambda. So you can keep the values 350 micrometer, so convert it into this meter, divided by wavelength is 800 nanometer, and we will convert it into meters. So meter gets cancelled. The answer is, let me do a quick calculation, it's 350. 350 into 2 divided by 800, which comes to be 0.875 into minus 6 plus 9, which will be 3. So the answer will be 875. So 875 wavelengths will be there inside in the cavity. So here, as you see here, you have, this is one wavelength. So like that, we'll have 875 wavelengths, or 876 number of modes. One wave, when you have half wavelength, you have mode 1. So when you will have 876 wavelengths, 875 wavelengths, you will have 876 modes. Okay. So this solves the question. Coming to the next one. So the next question is, among the following, the laser that has or have fundamental wavelength in the visible range is or are Heine laser, that is helium neon laser, Nd:YAG laser, titanium sapphire laser, or ruby laser. So let's see what are their lasing wavelength. Now Heine laser, helium neon, short form is Heine. Heine laser is 632.8 nanometer, as you saw in this question. Here 632.8, it's written in microns. Okay, maybe this is wrong because it is nanometers. Maybe the picture is wrong. I have taken it from the internet. Okay, so let's leave that. It is 632.8 nanometer, and Nd:YAG. So do you guys know the full form of this? It is neodymium. This is Nd. YAG is yttrium. Aluminium, garnet. Okay, so Nd:YAG, for Nd:YAG it comes at in the IR region. Okay, so next is titanium sapphire. For titanium sapphire, mostly it is operated at 800 nanometer, But this one is it's a tunable laser. Tunable means you can change the working lasing wavelength. Tunable laser from 650 to near IR, somewhere around 1000 nanometer, you can say. It's a tunable laser, but mostly operated at 800. Okay, and then next one is ruby laser. Ruby, it's very famous stone crystal. Ruby laser is 695 nanometer. Okay, so you see which one comes in the visible range, near about visible range. Answer will be this also you consider visible because you can tune it from 650. 650 is invisible, so you consider that this Hini. Nd:YAG is in IR. This one is IR, so it won't come. Titanium sapphire, yes, and then ruby 695, which is visible. So the answer for this question will be A, C, and D. It was a multiple select question. Okay, let's move to the next one. A mode-locked laser has a broad spectrum, is absolutely monochromatic, is pulsed operation, is continuous wave. So, mode-locked laser is always pulsed laser because we get pulsed laser because of the phenomena called mode locking. So, it will give pulsed laser only, right? So, let me draw a diagram over here. So, this is the baseline. I don't know how this pen will it let me draw or not. So it's not coming out good, but okay. Intensity is also got changed. Okay, increase it little bit. Very bad drawing. I cannot be better. Leave this. So just assume this is one. Okay. So we have, this is what we get as an output of mode locking. So you will get pulses. So you see it is what we are getting a very high, assume that this intensity is very high with respect to these. Very high means very high, that it will almost seem like 1, 2, 3. It will almost seem like a delta pulse. So here you have little bit these things, but these are very negligible with respect to this. Like delta pulse, like delta pulse. I am saying like delta pulse, but not exactly delta pulse, because they have some width. It is not a straight line like this. They have some width. So they have some width. This is their pulse width. So they are not absolutely monochromatic. So they have pulse width, and here in x-axis this is the spread, so it is not absolutely monochromatic. So this option, the option B, this one is wrong. It pulsed operation. This one is correct because mode locking, to get pulsed lasers only we do mode locking, or I can say mode locking gives pulsed laser only. So we will get pulsed operation, not the continuous wave. Has a broad spectrum. Yes, it has a broad spectrum. This is the spread. We are not getting one single wavelength. So we will get as a broad spectrum. And what we this part is called pulsed width, TP, let's say. And the distance between here to here, this distance is called repetition rate. After how much time, here the x-axis, this here it is time, x-axis is time, y-axis is intensity. Okay. So the distance between two pulses, sorry, the time gap between the two pulses is the repetition rate, or the inverse of time gap, I must say. Inverse of time gap is the repetition rate. Okay, so the answer to this question is has a broad spectrum and gives pulsed operation. Okay, let's move to the next one. So the next question is, I think it is the last question of the assignment part. It's a numerical question. For an amplified laser, power of 1 watt, repetition rate 1 kilohertz, pulse duration 100 femtosecond, wavelength 800 nanometer, the energy per pulse is. Now we have to calculate energy per pulse. I think I had given you this question in the last session. Let's do it again. Here the numbers are little different. So how we calculate energy per pulse? Or you guys will do it on your own? Shall I leave this as a homework? I think you can do it. So better to solve it here only. We will give some new questions for homework. Energy per pulse is equals to energy we are getting in 1 second divided by number of pulses coming out in 1 second. Number of pulses in 1 second. Okay. So energy in 1 second is what? Power. Because power is energy by time. Energy per unit time. And power is 1 watt. 1 watt is equals to 1 joule per second. So energy in 1 second is 1 joule. Divided by number of pulses per second. Number of pulses per second is the repetition rate. 1 kilohertz, that is 10 to the power 3. Hertz is second inverse. So it is 10 to the power 3 second inverse. So we have energy per pulse is 10 to the power minus 3 joule, that is 0.001. So this itself is asked in the question. So here the answer is 0.001 joule. But let's do a little more. Here so many extra info are given. Repetition rate, pulse duration, wavelength. So let's calculate the number of photons per pulse. It is not asked in the question, but for our practice we can calculate. Number of photons per pulse. This we can get from energy per pulse divided by energy of one photon. So how to get energy of one photon? Because we have been given wavelength. So wavelength ko we will convert energy in wavelength, we will convert into it energy. So it is hc by lambda. So when we will solve this, energy per pulse we calculated 10 to the power minus 3 joule divided by hc by lambda. So here it is 6.626 10 to the power minus 34 joule second, 3 into 10 to the power 8 meter per second, and lambda I am writing over here 800 nanometer, converting it into meters. Okay, so on solving you will get 40.245 into 10 to the power 14. That is, change the place here, almost 4 into 10 to the power 15 photons. So this is the number of photons will be there when one pulse comes. So one pulse hits the molecule, it means 10 to the power 15 photons are hitting the molecule. So much photons. And next thing we can calculate is the radiative power. Radiative power, radiative power per pulse means actually how much power is there in one pulse, which is energy per pulse divided by pulse duration. So energy per pulse is 10 to the power minus 3 joule, and pulse duration is given here in the question, which is 100 femtoseconds. So 100 femtoseconds you can write it in seconds, 10 to the power minus 15 seconds. So when you will do the calculation, it will be, it's just 10 to powers 10 to the power 10. 10 to the power 10 joule per second, which is 10 to the power 10 watts. So the molecule feels 10 to the power 10 watt power in 100 femtoseconds. Like at one go in 100 femtoseconds. So in 100 femtoseconds, this much power the molecule is facing. Okay. So I think we are done with the assignment, but as we have more time left, I have few extra questions for you guys. So the question 12 is, what is the need to achieve population inversion? So why do we want population inversion for lasing to happen? Because we want lasing due to stimulated emission, and for stimulated emission there should be more number of molecules in the excited state. So that's why we need population inversion. If there are more molecules in the top state, then only they will de-excite and come to the ground state at one go, right? So that's why we need population inversion. So when population inversion is there, most of the molecules are there in the excited state. So, to, so the answer to this question will be to excite most of the atoms or molecules. So when population inversion is there, most of the molecules most of the molecules are in excited state. Okay, and from what it will happen, we will get one by one photon will not come from the energy level E2 to E1 or the higher lasing level to the lower lasing level. If one by one photons will come, what will happen? The intense, we won't get that much intensity. So one photon will emit light, a small amount of light. 10 photons will emit light together. That light intensity will be more than what is emitted by one photon, right? So we want the maximum population to come down at one go so that the intensity of the light is so much. So that's why, and this situation is called amplification. So the light will get amplified. Instead of one photon, we are getting a large amount of photon, like 10 to the power 6 or 10 to the power 3 photons at once. So that's why we need population inversion. So this leads to amplification of the pump light or the incident beam. Okay, so the answer to this question is A, to excite most of the molecules or atoms to the higher energy level. Okay, so next question is calculate the number of photons from green light of mercury lambda 4961 angstrom required to do 1 joule of work. So it's a simple question. We know energy is equals to hc by lambda to 6.626 to 10 to the power minus 34 joule second, 3 into 10 to the power 8 meter per second. Lambda is 4961 angstrom, converted into meters. So upon calculating, it will come 0.00468 into 10 to the power minus 16, that is 4.0068 into 10 to the power minus 19 joule. So energy of one photon of this wavelength is this much, 4 into 10 to the power minus 19 joule. So number of photons required to do 1 joule of work will be, we can just simply divide 1 joule by this much energy. So number of photons required will be 1 joule we have to do work, and we have 4 into 10 to the power minus 19 joule energy packed in one photon. So this will into 10 to the power minus 19 joule. So when you will simplify, it will come around 2.4961 into 10 to the power 18. So this much photons you need. This much photons you need to do 1 joule of work, or 1 joule of, yeah, to do 1 joule of work. So the answer here is, everything here is in 2.1 into 10 to the power 18 we have here, and this one, this is wrong, so this is the correct answer. Answer for question 3 is B. Understood? Okay, So let's move to the next one. So this question, this is an easy one and you guys can do it. I'll give you 2 minutes. You pause the video if you are watching it on YouTube live, YouTube recorded lecture. You pause the video and then solve it on your own. I'll solve it after 2 minutes. So the question says, calculate the wavelength of radiation emitted by an LED made up of semiconducting material with band gap energy 2.8 electron volts. So here we have been given energy band gap, that is 2.8 electron volts, and we have to calculate the wavelength. If you guys can recall, we just did the assignment question in which we had been given the lasing wavelength 496 nanometer or something, and then we calculated from there the energy related to that wavelength. So sorry, this is just the reverse question, that you have been given energy and you need to calculate the wavelength. Now let's solve it. I'll go above and then you guys can see. You remember we derived this formula, energy in electron volts and wavelength relation in nanometer. So the formula was what? This much. E is equals to 1240 by lambda times lambda electron volts. So you can use the same formula here again. E is equals to 1240 by lambda, but remember this one should be in nanometer. It won't work here in angstroms, so you have to convert it into nanometers. Okay, sorry, we need to calculate the wavelength, right? So we will write lambda in nanometer is equals to 1240 by energy, and these two, everything is in electron volt. Here it is in electron volt. So we have 1240 divided by 2.8. Both are in electron volt. So on dividing you will get 442.85. But remember the unit should be nanometers. The unit should be nanometers. So the wavelength is 442.85 nanometer, that is into 10 to the power minus 9 meters, and then you can convert it into angstroms, which is 442 8.5 into 10 to the power minus 10 meter. So in angstroms you will get 4428.5 angstroms, right? So let's see which option it is. So we don't have any option exactly 4428.5 angstroms, but we have the option D, which is 4430.8 angstroms. So we'll choose the closest one, option D, 4430.8 angstroms. So here the answer to this question will be D. Okay, let's move to the next one. Question number 15th is, which of the following is the correct expression for the relation between Einstein's coefficient A and B? So this question also I think you guys can try on your own, and then I'll take a minute, I'll give you time. Try to solve on your own and then I'll solve. This also we discussed earlier in the same in the assignment questions. See, here I have given you the reference. From here you can find the relation between the Einstein coefficient. What we have to do? We just have to equate these two equations. We already know B12, B21 both are same and both are equal to 1. That is B12 is equals to B21 is equals to B. So this term is not here. It is equal to 1 here. It is equals to 1. So now this, the numerator part, when you equate the numerator to the numerator of the equation 2, what you will get? A21 A21 divided by B1, oops, sorry, B21 or B12, because both are same, is equals to 8 by h nu 12 cube divided by c cube, isn't it? See, here we have 8 by h nu 12 cube divided by c cube. So the answer to this question is here in front of you. The relation between Einstein's coefficient A and B is 8 pi h nu cube by c cube. Let's see, 8 pi h nu cube by c cube. It is the first option itself. This option here, it should be nu cube. It is nu square only. So this one is wrong. 8 pi nu squares and c square. So both should be cube. This is also wrong. 8 pi h nu, it's only nu to the power 1, but we have nu cube. So this is also wrong. Answer is A. This is the relation between Einstein's coefficient. And this is very important. Relation between Einstein's coefficient. Okay. So let's see what the next question is. Next question says, an incandescent lamp is operating at an operating frequency of 5.2 into 10 to the power 14 Hz. Calculate the ratio of stimulated emission rate to spontaneous emission rate. So we have to calculate the ratio. So from where we will get? We'll use the same equation. But there is one thing to note. What is A21? A21 is spontaneous. A means spontaneous. This is spontaneous. and B is stimulated. B is for stimulated. So this relation holds when the numerator is spontaneous emission, uh, Einstein's coefficient, and the denominator is stimulated emission, Einstein's coefficient. But notice that in the question it is asking the ratio of stimulated to spontaneous. So we have to calculate the ratio B by A, not A by B. So if you guys will do A by B, the answer will be completely wrong. So here this was the hidden thing in the question. Now let's calculate. We'll first calculate A by B only, and then we can just take the reciprocal out of it. So here A by B is equals to 8 pi, that is 3.14, 8 pi h, 6.626 into 10 to the power minus 34 joule second. Nu cube, nu by c whole cube we can write. So it is 5.2 into 10 to the power 14 divided by 3 into 10 to the power 8 and whole cube. Okay, so upon this term we can multiply, it will come 166 point into 10 to the power minus 34, and when you will divide this term you will be getting 1.734 into 10 to the power 6 whole cube. 4, 5 I am writing in short, into 10 to the power minus 34. Taking the cube of this part, it will be 5 point into 1 second, let me check whether the cube is correct or not. Seven, 3, 4 to the power 3. Yes, it is correct. 5.213 into 6 times 3, which is 18. So when you will multiply, you will get 867.678 into 10 to the power. This you will do minus 34 plus 18, which is minus 16. So this we get for A by B, spontaneous by stimulated, but we have been asked stimulated by spontaneous, that is B by A. So B by A we will take reciprocal 1 divided by 867.678 to 10 to the power minus 16. We will get 0.115 into 10 to the power 16. And writing it in the scientific terms, into 10 to the power 13. So the answer to this question will be 1.55 into 10 to the power 13. This is the ratio between stimulated emission rate and the spontaneous emission rate. Okay. So let's move to the next one. We have 15 minutes and 3 more questions. So we'll do it easily. So the next question is, the rate of change of intensity of stimulated photons depends on N1 is the population of ground state, N2 is the population of the excited state. So intensity of stimulated photons. Now from where we are getting stimulated photons? From the energy level E2. And you remember I wrote somewhere the rate, the decay of population at energy level E2 when we were deriving the relation between the Einstein's coefficient. See here this part. Let me write again. So I wrote dN2 by dt is equals to 0, and for that B12 rho N2 nu N1 is equals to B21 rho 12 nu N2 plus A21 N2. So this is the of rate of decay of population at energy level E2, or you can say rate of change of intensity of the stimulated photons. So intensity of stimulated emission will change by changing the number of photons in the energy level, by changing the number of molecules at E2 energy level. Okay, if there are less, if the population is getting less in the E2 state, we will have less intensity. So the two, intensity and population, are related. So you see here we are taking the population of N2 level and N1 level both. I mean N1 and N2 both. So in this expression both population are there, which means that the population at energy level E2, or the intensity of the stimulated photons, depends not on the population of the energy E2 itself, but also depends on how much is the population at N1. So here we got the answer that it depends both on N1 and N2. Okay, so the answer will be C, both N1 and N2. Okay, understood? Let me try to draw what is. This is E2, this is E1. It has a population N1, it has a population N2. So when you will, here the population, how much you will, first thing it will depend upon this intensity, how much is the pump light, but it also depends upon how many molecules are there in this. So if you are putting light, it will get excited, and we will get here maybe 3 4 photons, and these molecules will then get de-excite and will emit. So this is stimulated. So the population at E2 is decided by the population at N1 to some extent, and the stimulated photon intensity is determined by how many photons are there at E2. So it is in terms defined by both N1 and N2. So that's why the answer is both N1 and N2. Okay, I think now it is clear. Okay, so this is our second last question for this session. The question says the probability of spontaneous emission increases rapidly with the energy difference between the two states. The statement is true or false? Think about this statement for a moment and then I will give the answer. The probability for spontaneous emission increases rapidly with the energy difference between the two states. So I have drawn two diagrams. In the first one, the gap between E1 and E2 level is more, and the second one, the energy gap between the levels undergoing spontaneous emission is less. So what do you think, in which one the rate of spontaneous emission or the probability of spontaneous emission will be maximum or will be more? So let's go back to the relation between the Einstein coefficient again. What was the relation? A by B, B is stimulated, A is spontaneous. A by B is equals to pi h nu by C cube. So if we'll keep this as fixed, then you see A spontaneous is directly proportional to nu cube. Nu is the frequency between energy level 1 and 2. So as the frequency will increase, and it is cube, as the frequency will increase slightly, the amount of spontaneous emission will increase rapidly. So slight increase in the frequency, or as frequency and energy are directly related, so we can write slight increase in the energy gap will increase the spontaneous emission very rapidly. It will increase the spontaneous emission very rapidly because it is related by cube factor. It is not directly related. It is directly nu to the power cube. So here we have larger energy gap. Here we have del E1 and here we have del E1 dash 2 dash. As del E1 2 is greater than del E1 dash 2 dash, so here energy gap is more, frequency is more, so the probability of having spontaneous emission in this case will be more. Okay, more spontaneous emission. So here we will have more, here we will have less spontaneous emission. So the question says the probability of spontaneous emission increases rapidly with the increase in the energy difference between the two levels. This statement is absolutely true. Okay, as we will increase the energy level, we will have more of spontaneous emission. And we know that spontaneous emission is not desirable for lasing. So for lasing, what do we need? We need the less energy gap between the energy levels undergoing lasing, so that we will get most of the stimulated emission and not the spontaneous emission. Okay, is this question clear now? So let's move to the last question for today's session. The question says, Which Einstein coefficient should be used in this case? You see the diagram. This is the easiest question for today, I guess. After this much discussion, you guys are definitely able to do this. So what is happening? See in the diagram, we had one molecule in the upper energy state, E2, and then it was hit by a photon of energy h nu, the system, and then what is happening? The molecule which was here, it came back to the energy level E1 by releasing photons. This was the previous one and this which it released. And see, these two are collimated. What we discussed in the first question, this is coherent and collimated. So what kind of emission is this? Obviously, stimulated. Stimulated because we are stimulating the molecule, the system, to relax back to the ground state. It is not happening naturally on its own. We are giving it some energy and then it is coming back. It is coming back from here to here. So that's why it is called stimulated. And for stimulated emission, we use the coefficients B. A for spontaneous. A is for spontaneous. For spontaneous processes, the coefficient starts with A. Remember this. And for stimulated, the coefficient starts with B. And now see from where to where it is going. The start point, initial point is 2 and the final point is 1. So we first write the initial and then write the final. Here I am writing IF. This is for initial. For you guys to remember that which one you write first. This one is fine. So for this process it is coming from 2 to 1. So here we will write B2 1. B2 is the initial point, initial level, and then after after relaxing back to energy level 1 it is coming to 1. So B2 1. So here the answer will be Einstein's coefficient used in this case should be B2 1. And here how we will write the rate? The one last thing let's discuss. Here rate should be B21 and then population of this state N2, and also it will depend upon how much energy we are giving it to stimulate it. So it will depend upon the energy density also and this frequency nu. So the rate for this process will be B21 N2 rho 21 nu. Okay. So this is the answer for here. Okay, so we have discussed a lot of questions today. I think 19 or 20. So today we discussed assignment 4, weekly assignment 4. I'll end the session here. I hope you will watch the recording. No one is attending a live session, so I'm assuming that you guys are watching the recordings from YouTube. It's there, and the slides are also there in the Google Drive. And the link for both YouTube and the Google Drive you can find from the course content itself, from the NPTEL course. Okay, so I'll see you. So we will meet again next Friday with weekly assignment 5. I know the deadline for fifth assignment also has crossed, but because we are discussing one assignment at a time. So we will take up the assignment 5th next week. So till then, good night. Keep learning. Bye bye.